draw a cross-section profile. Geologists like to know what's underneath, what's in the ground, and therefore it becomes advantageous to somehow use a map to figure out what the subsurface may look like. Well, this little exercise will give you a hands-on experience in drawing a cross-section of a map and, with some geology, even figure out what lies below. Now, what's a cross-section? Well, we start with a topographic map, and it should have contour lines on it, like the one given in this example. That's our beginning point. Now, what we need to identify on the topographic map is a place where we want to slice the surface and look below. That's called a section line. Well, they're usually labeled with something X to X prime instead of just AB or CD. This way, multiple section lines can be put on one map. In our example, we use a line labeled A prime, a little tick mark on the A. We call this the A section. It goes across that hill you see in the southwestern corner and up to this place out of the valley in the northeastern corner. Now it's easier if my section line is horizontal. So let's just move the map and turn it around. What's next? We need to take some scratch paper and carefully fix it to the map along the section line so we can transfer our elevation points. Well, a piece of scratch paper works fine. And now everywhere where my section line crosses an elevation line, I'll put a tick mark and mark the elevations on my scratch paper. Point A is my starting point, and here we cross the 550 line, then the 575 line, and so forth, until we have the lines transferred with the correct elevation onto our scratch paper. Now, a word of warning. If you have some very steep terrain and very closely spaced elevation or contour lines, you don't have to write down every one. Sometimes it's good enough just to do the index contour. However, like in the center section of our A to A prime section, where the contour lines are spaced very far apart, it is wise to use every contour line and transfer the points. Not quite done yet. There might be some landmarks that you would like to transfer also. The assumed highest part of the map or top of the hill could be marked, as well as a stream valley. And give it a little tick mark. Well, now we need a blank piece of paper, or better yet, a graph paper. Graph paper has the advantage that we can transfer our elevation lines much easier. Okay, here's my piece of paper. Now, what is next? Well, we need to draw a vertical scale. Remember, we are slicing the earth open and look at a section, which means we're going to see the topography that is exposed in that particular vicinity. Now, why do we need to decide on a vertical scale? Let me explain. We're going to start with a map scale and just put it vertical. Here you have it, from 0 to 1,000 feet. That was the same scale that was on the map. And we transpose the tick marks for right now. The question is, should we really leave the distances exactly like that, from 1,000 to 0 feet? Well, there is a small problem. Map scales usually do not provide a high enough resolution for my vertical scale. Let me explain that a little bit. Here is a vertical scale as it would be drawn in accordance to the distance scale. You don't see much. It looks just like a straight line. However, by just exaggerating the vertical scale 5 times, another profile emerges. It shows the little bumps and valleys much better. We could go to extreme. We could really exaggerate it, let's say, 50 times, and this is what I would get. Now, every valley, every nook and cranny, if you want, is clearly visible and may be advantageous to give us some ideas of the geology below. Hence, we like to exaggerate the vertical scale. The amount of exaggeration is then stated on the vertical scale, so people that look at the graph or the cross-section you create are not surprised when they think it's a very steep terrain, that they know that you have exaggerated. Well, for our purposes here, and since our terrain is already pretty distinct, we just exaggerated 2 times, so we need twice as many tick marks on our scale. Well, that worked pretty good. Now, how are we going to decide on a scale? Well, if this little line you see from 0 to 500 would be the scale that is our map scale or horizontal scale, that scale would now 0 to 250. So the 1000 would be the 500, then we have it exaggerated 2 times. Let's label the tick marks accordingly. And here's what we get. We're going to get a 2 times exaggeration. Now we can also go below sea level. I started at 0 here, if we want to, because rocks reach much further down. Alright, we are about ready to transfer our elevations onto our graph. Well, and graph paper is usually very helpful. Now what you can do is you remove the piece of scratch paper from the map and place it just parallel to the graph paper. All that's left now is to transfer the points at their exact location to their respective elevations. Now it's important that your scratch paper is not wiggling or moving or shifting left and right during the process, but is held in place. Sometimes it helps to put a little bit of tape on it to keep it from wiggling and to give you an exact profile. Let's transfer the points. A was here, and it sits at 525. Well, 550 would be right there. My 575 right here, the 600 point right there, and so forth. I can do this with all the points and transfer them to the graph paper. You can see immediately that a beautiful 2 times exaggerated profile emerges. Let's put the top of the hill in place, which should be the highest point, between my 2 contour lines, and also the stream as the lowest point. All that is left now is to connect the dots. Again, don't use straight lines, but try to have a curve so it represents what nature really would look like. Voila! We got our profile now identified, and that is the surface as you would see it. However, geologists are interested in what is in the subsurface. So, what are we going to do with the profiles? Here is a topographic map with a section line drawn on it, and the profile shown below, and some arbitrary rock layers. These rock layers are horizontal, but you can see now that from the profile we can tell the thickness of these rock layers, especially the green one. Here's another profile with some more distinct rock layers. Not only can we see the stratigraphic law of lateral continuation through the valley, but we also can read of the thickness. Let's assume that the lowest layer contains an ore-bearing vein of gold, but I own a property to the far left of the property. How deep would I have to dig down? Well, with this profile, as you have drawn it, you can now tell how deep the shaft would need to be to get to the ore-bearing layers. What about a topographic map that also has some geology on it, like this one? Could we see what the subsurface looks like? Well, it is great if we had a few strike and dip symbols, like one here, one there, one here, and hopefully a few more that tells us in which way the layers are dipping. Well, after we have drawn all these, couldn't we do 2 cross sections and kind of put them together at the edge of my geologic topographic map? Well, That now gives us a beautiful picture of what the subsurface looks like. Let's say the purple layer, or KWB, is oil-bearing. Now you can tell exactly how deep you would need to drill the wells to get to this layer and to recover the treasures of the earth. Cross-sectional profiling is very important to geologists. We're trying to find out what's in the subsurface. Coupled with the geology, you can get a pretty detailed picture of what lies below that helps you identify stratigraphy, rock layers, formation thickness, tilts, folds, and even faults. I hope by learning how to draw cross-sections, you can now decipher subsurface geology a little bit better.